Standard electrode potentials are determined at 1m concentrations. However, cell potentials are concentration dependent. How can we determine the cell potential if the concentrations are not 1m? Walter Nernst was a German physical chemist who won the Nobel Prize in 1920. One area of his research was the concentration dependence of galvanic cells. The Nernst equation shown here allows us to calculate cell potential at non-standard conditions. E cell is the cell potential at non-standard conditions. E naught is the cell potential at standard conditions. R is the universal gas constant and T is the temperature in Kelvin. Also, N is the number of electrons transferred in the equation and F is Faraday's constant, 96,487 coulombs per mole. Q is the reaction quotient, or the ratio of products to reactants in terms of their molar concentrations. To calculate Q, the products are put in the numerator and the reactants are in the denominator. Raise each species to a power equal to its coefficient in the balanced equation. Molarities are used for concentrations as indicated by the square brackets. Remember that concentrations of pure solids and liquids are taken as unity. By converting natural logarithm into base 10 log and substituting the value of R, F and T equal to 298, the equation can be reduced as shown here. Let's work through a typical problem involving the Nernst equation. What is the cell voltage of a Daniell cell running with 0.1 molar zinc sulfate and 0.5 molar copper 2 sulfate at 25 degrees Celsius? The balanced net ionic equation is given here. Here's a strategy for solving the problem. First, you need to find E cell at standard conditions using our table of standard electrode potentials. Then, use the Nernst equation. From the half reactions, we see that 2 electrons are transferred in the overall reaction. Therefore, N equals 2. Now, we need to find E naught cell by using the equation shown here. E naught R is the electrode standard potential of a right-handed or reductive electrode and E naught L is the left-handed or oxidative electrode. Now work out the expression of Q, the reaction quotient. Since the concentrations of solids are taken as unity, the reaction quotient Q becomes the concentration of zinc 2 ions over the concentration of copper 2 ions. Then, we can substitute our expression for Q in the Nernst equation as shown here. From here, we can substitute our values for E naught, N, and the ion concentrations into the Nernst equation. The ratio for Q can be simplified as 0.1 divided by 0.5 equals 0.2. Now, it's a matter of simplification of the expression E cell is equal to 1.12 volts. pH meters also work on the principle of the Nernst equation. Here is a typical problem you might encounter. A hydrogen electrode is in contact with the solution with a pH of 9. What is the potential of the electrode? Let's work through this problem together. We'll start by listing what we know. Since we're told the pH is 9, the hydrogen ion concentration is 10 to the power of minus 9 molar. The equation for the hydrogen electrode is H plus 1 electron makes 1/2 hydrogen gas. We'll assume that the pressure of hydrogen is held at 1 atmosphere. From the equation, we see that 1 electron is involved, so N equals 1. By convention, the standard potential is 0 volts. Now we can substitute this information into the Nernst equation. From the equation for the hydrogen electrode, we see that Q equals H2 over H plus. By evaluating the equation, we find that the electrode potential is minus 0.531 volts. Let's start our discussion with the example of a Daniell cell. As a Daniell cell starts functioning, the concentration of copper-2 ions starts decreasing, and that of zinc ions starts increasing. It means that Q, the reaction quotient in the Nernst equation, is increasing. This shows that the cell voltage will decrease. At one stage, the concentrations of both the ions become equal. This indicates that the reaction will reach equilibrium and the voltmeter will read 0. For this situation, the Nernst equation can be written as shown here. However, at equilibrium constant Kc is equal to concentration of zinc 2 ions over the concentration of copper 2 ions. Substituting the values of R and F and of T as 298 Kelvin, we get the equation for equilibrium constant Kc as shown here. Consider a galvanic cell made from half cells using magnesium and nickel. Notice that the ion concentrations are all 1 molar. What is the equilibrium constant of this cell? Try to solve this problem on your own before proceeding. Let's start with the half reactions to find E cell. Since nickel has the greater reduction potential, it is the cathode and magnesium is the anode. By substituting the standard reduction potential values as shown in the equation here, you can find that E cell is 2.11 volt. You can rearrange the equation that relates E cell to the equilibrium constant to solve for the log of Kc. You should memorize this equation. You can then substitute your information about this cell into the rearranged equation. Log of Kc is equal to 71.5. To find Kc, you can take the inverse log or the exponential function of both the sides. This gives us a value of 3.16 into 10 to the power 71 for Kc, an extremely large number. It is also possible to derive an equation relating the Gibbs free energy and the cell potential. The equation is shown here. This is another equation that you should memorize. Note that standard cell potential is an intensive property, but the Gibbs free energy is an extensive property. The value of delta G depends on the number of electrons transferred. You already know that the Gibbs free energy is related to the equilibrium constant by the expression delta G is equal to minus RTLNK. With these equations, you can easily calculate the equilibrium constant and the Gibbs free energy for a given electrochemical cell. Let's consider a galvanic cell at 298 Kelvin. This cell is made from half cells containing aluminium and zinc, where the ion concentrations are 1 molar. From the table of standard reduction potentials, you can easily find that the standard cell potential at these conditions is plus 0.90 volt. We first need to look at the balanced equation. Since zinc has the higher electrode potential, zinc undergoes reduction, while aluminium undergoes oxidation. Notice that 6 electrons are transferred in the equation. 6 electrons are lost to oxidize 2 aluminium atoms to aluminium ions. Therefore, N is equal to 6. You know that delta G is equal to negative NFE cell. You can substitute these values in the equation. We get the Gibbs free energy is equal to negative 521 kilojoules. You can find Kc from E cell. Start with the equation relating E cell and Kc. Rearrange to find log of Kc and substitute. Log of Kc is equal to 91.525. So, we end up with a Kc value of 3.350 into 10 to the power 91. With the galvanic cell, the cell potential is always positive. It means that the Gibbs free energy for a galvanic cell is negative, which is consistent with a spontaneous process. A spontaneous process favors products. So, we see large values of the equilibrium constant.